Hi everyone, thanks for joining us. We'll just hang for a few minutes and just wait for others to join before we kick off. Hi to those who've just joined us. We are going to just sit tight for another couple of minutes just as others make their way in, and then we'll kick off. Alrighty, I might kick us off just with some housekeeping, just as others join. So thanks again for coming to another one of our virtual brown bags. As you will have seen from the comms, we've moved from Google Meet to GoToWebinar. So just bear with us today on a new platform, but I think we've got it all sorted. So just in terms of how it works for those who perhaps haven't used GoTo before, everyone will remain on mute. And if you have any questions, you just submit them via the questions panel on the right-hand side, and we'll go through all questions and answer them at the end with Maryna. For the next session and all sessions moving forward, they will be shared on the Eliiza Brown Bags landing page that we've set up. So that's where you can see the session info, and then also if you have anyone else that you think could value being part of these sessions, share the code with them and they can sign up as well. So that's on the right. All of these sessions are recorded and then they go to our YouTube channel, which most of you probably already know. And then thank you to everyone who threw their suggestions in when they registered for this next round of the series. So we've got lots of great topics coming up. So as always, share them with us if there's things you'd like to hear. So I'll hand over to Maryna, our presenter today, and we'll get started.
Thank you, Kate. Just confirming that you can hear me.
Sure can.
Cool, thanks. All right, so just to continue what you just said, if you're also interested in working with us or you want to explore this topic a little bit further, feel free to reach out following this email address. We can cover topics such as productionizing your machine learning solutions, a lot of data science related topics, or training and just general exploration, whether you want to explore it for your business or if you want to just suggest an idea for another brown bag session targeting your specific area. So I will now jump to my title slide, which is, could you repeat that, understand customers the first time? I'll start with introducing myself. So my name is Maryna. It's my second month at Eliiza. I am a data scientist. Before that, I worked at KPMG as a data scientist as well. And prior to that, I was a data scientist at a startup that works in the space of speech analytics. And my background is in physics, which is not necessarily relevant, but I did my PhD at Swinburne University of Technology, and it was in the area of computational physics. My very first project at Eliiza was very related to the work that I was doing at a startup 2 years ago. So I thought it would be a good idea to just round up all the bits and bobs that I learned along the way that are related to speech analytics, a little bit about automated speech recognition, speech to text, and also what you need to know in the context of a contact center. So hence this very light on any theoretical details topic. I really hope that you will find something interesting and will learn something new. I organized the session as follows. First, I'll talk about the very, very broad details about what is the data that we're working with, what is sound, how it is transformed in the contact center domain, what to expect and what to consider when you choose a speech text provider, what are those providers, and in terms of contact centers, what are the areas that they focus on, and how speech recognition and speech analytics can help. And finally, I'll conclude with a few remarks on what to be aware in terms of security and privacy when we work with this type of data and other data science considerations. So when we talk about speech to text and speech analytics applications, probably the very first thing that jumps to mind is virtual voice assistants in handheld devices or smart homes, so smart speakers. There was a study that showed that using voice is 3 times faster than actually typing. So Dr. Ian Pearson, the futurologist that is behind inventing SMS, he believes that we will certainly move to using voice interfaces more and more. And here I have just a few examples. It's a non-exhaustive list at all of how we use speech to text in our real time and speech analytics as well, our life, and not necessarily real time in our life, and how we interact with that. So I mentioned smart devices. Another example would be searching large volumes of information. So for example, a relatively recent feature of Google and YouTube. So YouTube produces automatic captions, and Google, because they are timestamped, you can now search that very easily. And it is a fantastic application because we have so much data that is in audio format, audio or video format. Another example that hopefully not many of us are familiar, but it is very valuable, is automatic captioning for people that have hearing problems. So transcribing pre-recorded content is very useful. Fact checking, we all know what wonderful era we live in of fake news. So transcribing that and quickly fact checking the content, the claims made by politicians or anyone is really valuable. And this also relates to media monitoring. A few years ago, there was a conference in Melbourne, and one of the it was on computational linguistics, and one of the presenters was from University of Edinburgh. So he contributed to SumUp project, and the idea was that you take continuous streams of news and you transcribe it and you group keywords or topics, named entities. This is intended to simplify work and life of people who actually do this on a regular job basis. So people would actually watch 4 streams of news at the same time and try to pick up all the emerging trends. And it's a tough job. And finally, contact centers. We all familiar with navigating when we want to reach to a specific department within a call center. We would press buttons. So this is known as interactive voice response. Instead of pressing buttons, we can be using our voice, and the system will transcribe it in the background and direct us to the right destination. And I want to emphasize, I'm not talking about using your voice for authentication. I'll talk about this a little bit later. And broadly, in terms of contact centers, using speech to text and speech analytics opens up many possibilities to optimize their processes and identify areas for improvement. Why would we care about call data in general? Well, because it is very important to understand what our customers are contacting us about. The data is really, really ubiquitous, and despite all of the advancements in trying to come up with ways to deter our customers from contacting us, directing them to self-service options, chatbots, and so on, people still, many people still choose voice communication as their primary choice of channel. And this data is very unstructured, so it's hard to analyze it without any additional steps. And it has several dimensions for analysis. So first of all, it's the way people talk. And second, it's what they say. So by transcribing that and analyzing, we can derive many insights. So what is sound? I'll just very quickly dash through all these details just to give you a little bit of perspective of what we're dealing with. So as we speak, our vocal folds produce waves that are pressure waves. So as we speak, we move air particles away and towards us, and this creates areas of higher and lower pressure, which can be measured by devices such as microphones, for example. I want to just briefly mention that when we start learning signal processing, typically we would work with such simple waves as a trigonometrical wave like cosine or sine. In reality, human voice is a very, very complex entity, a very complex thing, and it is much harder to analyze it and use than just a simple plain wave. So in general, a sound wave would be quantified using such features as frequency. So how many wave cycles we have per 1 second, and also amplitude. So amplitude identifies or indicates the volume, so this loudness of our sound, voice or sound we make. So frequency is measured in hertz, and amplitude or loudness is measured in decibels. There's a thing called fundamental frequency, and it is one of the features that characterize our voice that can be used sometimes to identify speakers, so diarise based on speaker, different speakers. So typically, it may ring a bell, so female voices have high pitch, so greater frequency, while male voices have lower frequency, and therefore they're seen as a lower pitch. So when we capture our voice or sound, we perform a number of sampling. So, Bureau of Meteorology would sample temperature. So they would take temperature measurement 10 times a day, or let's say every hour. So they have 24 samples. With audio, would do a similar thing. We would sample it. However, the sample rate is much, much higher. So as we speak, the voice signal is continuous, but when we capture it, we produce a discrete digital signal, which is characterized by the sample rate. I have a few examples of open source tools and libraries that are useful when you work with audio processing. So FFmpeg is an open source command line tool that is really useful when you want to read headers of audio or video files and understand what are the parameters of this file, or perform any manipulations like splitting channels, joining, or slicing audio. Audacity is a very nifty, powerful tool that is extensively used for audio and for audio editing, and it comes with some support for feature analysis. And finally, Sonic Visualizer, which is similar to Audacity. I personally use Sonic Visualizer for one application where I used a machine learning model to segment audio, so split it into some chunks, and I segmented based on speakers. And then you can import this data into Sonic Visualizer and can have this visualization, representation of your segments straight away. I'm not sure, maybe you can do this with Audacity. I use Sonic Visualizer for that. And Python library, so if you're using Python, you have many tools for importing, so reading an audio file and performing some analysis. So SciPy is a very powerful library for signal processing, and it comes with features starting from reading a WAV file and all the way to performing signal analysis and various transforms. Other noteworthy libraries are Librosa and PyDub. So PyDub can be used for segmentation, and Librosa has functionality, so methods for specifically perform audio analysis, like determining fundamental frequency, for example. So when we talk about signal features, so we want to build some kind of model or we want to extract features for our speech recognizer, what are those features? So here is an example of waveform of an audio. So Mozilla started a common voice project, I think back in 2017, I'm not quite sure, but the aim of that project was to source as many voice samples as possible to create a public domain data set, and the ultimate goal was to train an open source speech recognition engine. So I took a sample of a recording from that data set. Here it's a male voice saying, "I couldn't stop staring at it." So this is how it will look like when you load it with SciPy. And it is nothing less, nothing more than a waveform. So on the x-axis we have time, and on the left we have amplitude. And I want to note that amplitude is, it can vary. So the scale, it can vary because it would depend on the sample depth or the format of your audio. So by itself, it's not very useful. We do want to extract more information. As I mentioned, human speech is not as simple as a simple sine wave. It's a combination of multiple frequencies and multiple signals, if you will, and to decompose it into frequency components or to move to frequency domain, will perform a Fourier transform. And the figure there in the middle shows the spectrum of our audio. And what it shows you, again, on the X we have time, and on the Y we have frequencies, and the color scheme represents intensity or loudness or energy. So the brighter, brighter is probably not a good idea, but on one end we'll have higher energy, on another one, on the other end of the spectrum we'll have a lower parameter. So with the metrics that we can derive, so just from the time-based representation, we could look at zero crossing rate, and this is the we'll calculate the number of times the wave actually crosses the zero line. This could be useful for information retrieval. Signal to noise ratio expresses the quantifies the quality of our audio. So if we have a lot of noise, it will manifest in this feature. Fundamental frequency, which I already mentioned, and what it is basically the lowest frequency present in our spectrum, and it can be used for biological sex profiling. And finally, null-frequency substring coefficients. I knew that I will not be able to voice the definition, so I copied it here. But basically what it does is it is a representation or approximation of a human auditory system, and it is a null-frequency scale is a perceptual scale of pitches. And the idea is that as well, our auditory system is less sensitive to higher frequency sounds. So basically, as we move beyond 1 kilohertz frequencies, we start discerning them less and less. So this scale is representing that. And the coefficients are used as features, very often used as features for speech recognition. So speaking of speech recognition, this is a area of research that goes as back as to the middle of last century, and the early systems were very modest, and they were looking at a limited number of words, and all they were doing is looking at power spectrum and trying to find something that looked familiar and what they were expecting to see. This changed with the publication of the Soviet Academy of Science published dynamic time warping algorithm, which expanded the application of speech text to basically identify similar spectrums that belong to words spoken at different rates. So that kind of allows you to scale and disregard the speed of the same word. Then in the late 70s and early 80s, a big breakthrough was the application of hidden Markov models to speech recognition. And two students, James and Janet Baker, went on to create Dragon Systems company that was aiming to commercialize the technology. And they was very successful up until early 2000, when they were acquired by Nuance. And Nuance is another big player in the speech recognition market. And it is believed that even early Siri was actually using licensed software from Nuance to recognize speech. Then in 2007, Google launched this voice business directory search, where people would call and request some information about businesses. And despite the usefulness of the project, it didn't last long, and it is speculated that the whole purpose of the project was to gather as many voice examples as possible to later use for training voice recognition models. And finally, the last decade has seen a very rapid rollout of speech-to-text applications, and people are getting more and more comfortable to use it in their everyday life. Typical speech recognition systems consist of several building blocks, and I'm talking more about the traditional ones. So they'll start with ingesting the audio and potentially pre-processing it through the noise and might be normalized in some ways, and then extract some features. And use a decoder to produce the output. So decoder is the heart of the speech recognition system because it's sometimes referred as a speech recognition engine, and it combines various models to decipher the signal. So in traditional systems, there are 3 main models that I used for recognition, and these models are trained and maintained separately. So from a maintenance point of view, it's a bit of a problem. So that explains why many modern focus is to move to end-to-end development, so that all you have is the original audio and all you have at the end is the transcription. So the models are acoustic model, which is mapping audio features to phonemes. Phonemes are the smallest bits of language sound. So in English, it would be around 40. So there's not too many, around 40 sounds. Then pronunciation models would map these phonemes to words, and typically it's not a very complex system. It would be like a dictionary or a lexicon, which is quite static. And finally, the language model, which is an anagram model. It basically determines if the sequence of words makes sense. So I eat apple is much more probable than an apple eats me. So this is how language model corrects any or finds the right sequence of words. And because when speech recognition task is performed, the audio is split into small buckets of around 10 milliseconds. Those little buckets of signal can be seen as a stationary process. So that's why we can apply hidden Markov model, because we know that we assume that the next step only depends on what is said right now. And I have here an example that I found in one of the presentations of a speech recognition lattice. So when you work with speech, the output of a speech recognition system, sometimes you can come across alternatives, and usually it's just a list of one element, but it can have several alternatives. And the goal is to basically find the most optimal path that sequence of words that produces that is likely to have originated from the original sound. And these lattices can be quite big. Now, when we start working with speech analytics in the context of a call center domain, there are a few things that we need to be aware of. Whether you work for an organization that has a contact center, or you have a client that approaches you and they have a contact center. So the first thing you would want to know is what are the telephony and recording providers, because this information would likely inform you of what are the possible factors that apply to or affect the audio quality. So in telephony systems, because they're not music, they're not recording music, they record conversations over a very noisy line anyway. Sample rate is typically on the lower end. So I think for music CDs, it would be, I think between 40s and 50s kilohertz, 48 or something like that. Whereas for speech over the phone, it's 8 kilohertz. Many speech recognizers are geared to work with this sampling rate. However, if you have access to a higher sampling rate, it's always a good idea to use that because it will likely produce higher accuracy of speech to text. Whatever you have, do not resample. So do not switch from higher sampling rate to lower and the other way around. So when you work with codec, so encoding and decoding your audio, compressing, decompressing, just make sure that you follow lossless to lossless pattern rather than lossy to lossless and lossless to lossy, because you don't want to affect the quality of the audio.
Sample depth is also quite important, so make sure that it is 16 or 32 bits, and the higher is typically the higher end is preferred for speech recognition applications. When you convert from different media containers, it's also a good idea to stick with those that are not lossy. So for example, if you convert from WAV to MP3, probably perform speech recognition prior to conversion. And the same goes for codecs, so compressing the audio. When large volumes of information are produced, it's of course very important to manage the size of the storage, so that motivates the compression of audio. However, if you intend to transcribe it later, maybe transcribe it first and then compress. This is something just to have in mind when you start working with the historical data. Usually it has been already compressed, so just be aware that this is something that can affect the quality of transcription. In the context of contact centers, another thing to have in mind is the number of channels. So in older systems, it's typically one channel, so it is called as mono. And what it means is that both of your speakers, so the customer and the agent or consultant, will be on the same channel. And this could be a problem because you don't know who exactly said what. So be wary of that. The better scenario is when you have two channels, so stereo, you have the left channel and the right channel. Just keep track on who is on what channel. So if you have inbound calls, you may know that your agent is always on the right channel. And finally, when you submit calls for transcription, it's a good idea to submit them as they are without trying to apply any noise reduction techniques, because it would most likely be already included as part of the speech-to-text pre-processing. So for them, it's better to work with the original signal. So what do you need to be aware or consider when choosing a speech-to-text provider? There's a few items. So you do want to understand what is your use case, and depending on that, whether you want to process a batch of historical calls, that's one thing. But if you want your application to work in real time, it's a totally different story. So you need to make sure that your speech-to-text provider supports either of these applications. And typically, batch processing is like most will have it anyway. It's the real-time transcription that you need to double check and make sure that it matches your expectations. I already said diarization. So if we have just mono, and it is really crucial for your application to be able to tell who said what, then it is a good idea to check with the provider if they diarize based on speaker. So what that means is that they'll use some pre-trained models on voice feature, so they'll use fundamental frequency, things like that, to discern between the two speakers. Be careful though, because sometimes when it is machine learning trained model, it could produce unexpected results. I once had a call, transcribed call with speaker diarization that had 36 speakers in the same call. So just be wary of that. I think Google speech to text offers capping the number. So you say, I know suddenly there's two speakers, but still be careful with that because, oh no, sorry. My smart speaker just picked up Google. Yeah, so be careful with, this provider. They offer to cap the number of speakers. So you say, I have two speakers, although if there are transfers in the call, this may be a little bit confusing, but the same goes for channel diarization as well, because whichever channel is freed for the new speaker will be confusing as well. You want to understand what are the supported input and output formats. So the input formats would likely be an attempt of the speech text provider to exclude some codecs that they wish to avoid working with. So some codecs are proprietary, so you need to have special software to decode and something to be aware of. And in terms of output formats, it's something for you to consider. Like some speech to text providers would output just plain text, so plain text file with a dump of text. Great, but if you do want to do some analytics on top of that, you do want to have as much information as possible. So you want to keep all the metadata, and I'll show you a little bit later the example of a typical output and which fields I mean. Casing and punctuation. So some models are better, or some providers are better than others at recognizing punctuation. So full stops would be recognized based on silences. So if the silence is really long, it will understand that there's a full stop. Some are still struggling, and for us data scientists who work with this text, sentence boundary identification is a tough task. So it's better to have that information derived from audio. Support for custom vocabularies, that is also very important, because if you have a very specific domain, or you have some terms or abbreviations that is important, maybe it's your business name or the name of the business in your contact center, or your contact center, you do want that to be transcribed properly. So you would want the speech to text provider to support those features. So they would offer you to submit a file with the list of words that are important. And what this will do in the background, it will basically tweak their language model so that it will not discard this transcription just because it doesn't know what it is. Sensitive data. So depending on which domain you operate in, or your customer, being able to redact audio is potentially an important feature to consider. So some providers offer this as you do transcribe it and then retrospectively redact the audio and the transcript. And I'll mention a few things about it later in the session. Localization, so languages and accents, these could be also important, and even language models. So recently I worked with Google Speech to Text, and I learned that they have a phone-based language model. So it's, sorry, not language, phone-based recognition model. So it probably includes some noise pre-processing and is geared towards audio generated through phone. So if you plan to localize your application for I don't know, other regions where there's different variations in English or other languages altogether, it's a good idea to verify with the provider whether they support it or not. And maximum duration, it used to be a thing. Some are still imposing these restrictions on the audio length, but I think at the moment it's like 4 hours, so it should be well within the limits of your example calls. I hope no one has calls that are longer than 4 hours. Next thing we want to know when preparing for speech to text and further applications and speech analytics use cases, we want to know how long it will take to process. So let's say a customer comes to you and says, I have 107 of calls and they are about 10 minutes. On average, you do want to be able to estimate how long it would take you to process and how soon you can produce any sort of results. So in batch processing, it is quantified using real-time factor, and this is a number that tells you how long it would take to transcribe a file. And typically, that's a very approximate figure, but typically it's on a matter of 0.5 in that range. And what it means is that if you have a 10-minute audio, it will take 5 minutes to transcribe it. Now, it's different for batch processing, real-time processing, because in real time, we won't be looking at the real-time factor, we'll be looking at latency. So what is the delay between the person saying something and the transcription appearing? You know, when you watch YouTube and you see captions, there is a little bit of a lag, and this is known as latency, and it's typically around 1 second plus minus. And the reason for that is that you actually need to buffer a little bit of audio before you can process it. And lastly, the important bit is about accuracy. So let's say you want to pick the provider that is most accurate for your use case. What to know? First of all, the accuracy of transcription is quantified using word error rate. I think I don't need to mention, but I'll mention just in case. If you're choosing between, let's say, two providers, it's not enough to check the number that one provider provides or lists on the website and another, because they would be generated using different inputs. What you want to do is try them on the same file and decide it for yourself. And probably it's a good idea to have your file that is very representative of your domain setup. And in terms of items that are affecting the accuracy of transcription, of course, the audio quality. So the microphone, so the device that captures the audio, the signal, it has to be, it is suggested for it to be hand mounted, because otherwise it will be varying. We had a case, I came across a case where consultants in a call center were using all sorts of different devices. Some people were using AirPods as their tool for work, and it was producing just very varying levels of accuracy for different operators. One thing I just forgot that I didn't mention is calculating word error rates is a tricky task, because tricky and sometimes expensive and time consuming is because you need to have the original original text. So be it something that a person would read, or you would actually use human powers to transcribe it and use it as your base, and then measure insertions, deletions, and swaps of words in the transcription produced by a speech-to-text engine. So that's why it's a bit of an ordeal to calculate, assess accuracies. And going back to the factors that are affecting the accuracy, speech quality. So if a person is mumbling, that could be problematic. It could affect the accuracy. Background noises and crosstalk. All of the noises, everything that's like, if another person starts talking with me at the same time, we will pollute the signal, and it would be very hard to recognize that areas of overlap. That's why in mono calls, it's tricky sometimes to correctly transcribe what a person said if somebody was saying talking at the same time. The recording setup, so if you have echo, again, that is a noise that will just be recorded as well and distort the signal. Accents, many modern models, many modern providers, they would try to accommodate for various accents. So sometimes they would have a British model or US model, which would take into consideration various ways of how you can pronounce, use pronunciation, have various pronunciations in an audio. And some providers would even have like a global English model where they just blend everything. So probably just all the training label data is used, and the model is just everything is English. Thinking out loud, this was one of the factors that I saw on one of the providers' frequently asked questions page, and this is probably when you don't speak very coherently and you just form your sentences in a way that differs from what a language model is used to. It could say, I don't think that's right. I'll just swap those words because it's more probable that you are going to say this. And as mentioned above, sample rate and compression would also have serious impact on the quality. So what are the providers? If you are at the stage where you're choosing a speech-to-text providers, there are roughly, well, I divided them into 3 categories, so cloud providers, non-cloud, and open source. And probably some of you would be already familiar with cloud providers and their advantages, which include relatively, like if you're already using a platform, maybe you're using Amazon Connect, so plugging in Amazon Transcribe or the new Amazon Contact Lens feature is reasonably easy because you already have your data there, and they typically come with easy to understand billing models. However, they can get a bit complicated if you don't know, for example, what are the volumes of audio you're going to transcribe. The negatives would include they're quite limited to what they offer, so it's unlikely there'll be a lot of space for customization or meeting your specific requirements. And if you don't use those platforms, migrating the data, or if you want to stop using the platforms, migrating your data off the platform could be quite a challenge. In terms of non-cloud providers, they offer greater, so there's more options, and they offer greater flexibility, and they allow you to pay as you go, but you get to manage your data. And you can deploy it in private cloud, which could be very useful for some institutions in the financial domain or health domain. The downside would be managing licenses. So you have to track the state of your appliance and making sure that you don't run out of hours dedicated for your instance. So that could be a bit of a nuisance. And finally, open source providers, they the list is not complete, but I was just looking at options in English. So the advantage of open source would be greater flexibility because you can dig into the code and understand what's happening and maybe changing it a little bit. It is most likely free. However, you need to understand that you still need to pay for the compute power if you choose to run it on any of the platforms. The limitations would include potentially limited support for sure, but also likely limited language selection. So English is great because many applications use geared towards working with English, but if your application involves other languages, could be a bit of a problem. And I think it's probably a speculation, but maybe accuracy is going to be a problem as well, because it's natural to assume that the people behind those open source libraries, they just don't have access to enough data compared to those gigantic providers like Amazon and Google. Here is a very simple output file of an automatic speech recognition. I took it from Amazon Transcribe documentation. The schema would differ from one provider to another, but the general idea is about the same. You commonly will get a JSON file with some key value pairs, and one of the most important ones is tokens or words. So you do want to retain as much information as possible. So the string itself, so what was the word that was spoken, whether it was punctuation or an actual word, you can tell that sometimes it's useful. The timestamps, and timestamps are really important because they opens up possibilities to reconstruct the conversation and know who, like if you have two speakers, you can easily map out the entire conversation and understand who was saying what, was the person interrupting, was there an unexplained silence in the call. And also another field in the output would indicate speaker attribution. So sometimes it could be a speaker specifically per word, or sometimes it could be like in older systems, they would give a list of tokens by one person, and then there'll be a special token indicating the tone that says tone, and then you know that the next blob or next list of elements is attributed to another speaker. It was a little bit clunky, but it worked. I'm sure the provider is working on improving that. So when you, if you're a data scientist and you need to work with the output of a speech recognition system, what you want to do is you want to spend quite a bit of time on thinking about your data model and thinking about what methods you want to have. For example, you want to have one method that, just give me all sentences spoken by one person, or give me all sentences that occurred in the first 30 seconds. So you do want to make sure that this is thought through and is reusable, so that you don't have to, iterate over lists over and over again. And in terms of contact centers, so what are the main applications of speech recognition and speech analytics in contact centers? First, I want to mention that many telephony providers nowadays are actually including speech analytics as part of their offering, so that if you are already running a call center, you may as well have additional features that would provide some insights into the into your contact center. And in terms of main area of focus, they are about roughly these three domains. So we want to focus on customer experience and customer journey, and automation and training, and compliance. So in terms of customer journey and customer experience, so for example, you do want to understand what are the main call drivers, like why are people calling? Sometimes just mapping to call queues is not enough, because somebody can just not follow that properly, or jump to the very first one just to get connected as soon as possible. So understanding why people are calling is important, and what it can return is you identify areas for improvement. So you identify automation outliers, so you know that, oh, maybe I need to add additional feature or additional dialogue flow to my chat board, because it appears to be important for people. In terms of automation and training, that focused quite a bit on the fact that the volume of data that is generated is so huge, and identifying those instances where maybe the sentiment was not so good, and the agent could benefit from a little bit of training, or this situation can be used as an example for other staff members. This is a great application, a good example of how you can apply it by providing a 100% coverage and trying to rank those goals. And some companies in the speech analytics domain offer this automatic scorecard feature. And finally, proactive compliance. And it is very similar to the quality monitoring, but in the sense that you still want to cover 100% of your calls, but you focus on something very specific that is required of you by the regulators. And speaking of regulators, a few years ago, ASIC, who is the main regulator in Australia for financial licensees, they looked into using speech analytics for analysing calls in the direct life insurance domain and figure out whether right sales practices were used. So this was this trial, and 3 demonstrators got to present how the solutions can help identify such goals. It was back when I worked at this startup that actually was one of the demonstrators, so I got to contribute to this project. And 2 years from now, so from then, it's still a very important topic. So ASIC is modifying their regulations and updating them very regularly. So there's a new regulation that comes into effect next year. And what it does, it redefines the, rewrites the definition of complaint. So now organizations that are subject to this regulation need to recognize social media posts as a complaint. Everything that happens in the contact center conversations can be a complaint, and the companies are requested to record them. And the time frame for resolving these complaints is now reduced by almost 50%. So it really cuts down the time for resolution. And here at Eliiza, in partnering with Google and our sister company Kasna, we were approached by a big insurance provider who wanted to trial how voice analytics can help in identifying complaints. And we developed a pipeline for transcribing audio calls and performing some analytics to help and localize this calls that require further investigation or follow-up. So if you are an ASIC, if you're regulated by ASIC, automating this process could be a great advantage for your business and help increasing the coverage. And finally, to a few words of caution. The technology side is great and it is evolving, but as users of the technology or users of the systems, there's a few things to be aware. And first of all, it's the privacy and personally identifiable information protection. So when we have audio and transcription, we now have two streams of data that potentially needs to be redacted. So keep this in mind. When working with reduction, many providers would, what they do, they would take audio as it is, transcribe it, and then use named entity recognition models to identify entities and then retrospectively redact it. Be careful with that, because you need to know what kind of information, like what are they giving sentences, words, or shorter snippets, or the entire transcript for named entity extraction. So making sure that if you provide enough context, that should work reasonably well. And that also, it's a good idea to check which models are used for named entities and or ask questions. For example, there's a library open source by Microsoft called Presidia that looks at sensitive information detection, and it is trained on the US domain. So it would have social security numbers or formats of phone numbers that are very different from Australian context. So be wary of that. One other note is that the Office of Australian Information Commissioner says that voice, so recorded voice, could be a personal information. So one thing to remember, that it's not just the customer, but also it is the operator that takes a call. So we just need to make sure that it is treated appropriately and with respect. And as data scientists, we must be really careful with recognizing the limitations of the technology, because if we're building some kind of scoring or scorecard that would rank calls based on agents' performance, for us, we want to achieve greater accuracy, but we have to be mindful that if the technology is suboptimal, this may actually impact somebody's paycheck. So we need to make sure that operators are treated fairly and there's no that they're not disadvantaged by technologies that we produce. And finally, a few other examples that are not necessarily what are relevant for call centers. They can be, but first of all, in terms of security, there are a few applications of speech recognition or a few methods that can be applied with malicious intentions. So one example is the adversarial examples where a speech is, so the audio is distorted so that the person cannot hear the difference, but for a speech recognition engine, it will send a completely different message. So it will transcribe it in a completely wrong way. And for example, smart devices, you can code an audio that will say, hey Google, open the front gate, and for you it will still sound as a, I don't know, an audio, a podcast. So this is something to be aware of, or to know. We haven't seen this in the news, so it's probably so far a good indication, and that it's not not a prevalently used technology. Another example is voice deep fake for scamming some people to pay money because they led to believe that this is a legitimate person requesting this information on money, and using voice as a biometrics for authentication. So authentication the person while they wait and they say, my date of birth is this and my address is this, and verifying this with your database is one thing, but authenticating using the voice, so, HSBC, we're using my voice is my password, so you say, and the engine authenticates you. This could be problematic for various reasons, but also because our voice age our voices age, and if we don't talk to the bank very often, it may lock us out, not lock, but limit our access to the system using voice. So something to keep in mind. And finally, I am concluding my slides and happy to take any questions.
Maryna, can you see the questions, or I can read them out?
Questions? I don't see the questions.
I've just got them here. But
Okay.
a question from June, and apologies if I have your name wrong. Is there a way to gauge customer sentiment from the audio signal, for example, an angry customer, directly without being transcribed first?
Great question. Yes, I don't see why not. So with audio features, you can have energy and that would, so for example, loudness, or you can say that, oh, somebody is really loud, it must be because they're yelling. The question would be training these models, so training the identification. So in terms of segmentation, that could be a problem. So I used, for example, there's a in a FOSS, I think the model, so it kind of identifies the number of speakers. And sorry, this is not exactly related to your question, but it's kind of along the lines. So that was something that I used to identify the number of speakers. So by having just one speaker in the call, I was able to say that, oh, the other person's really quiet. So from that information, you can gauge the quality of the audio, or you can say that the person is probably well, I don't know, quiet for whatever reason. So yes, there's plenty of things that can be done with audio, but it comes down to the definition of how exactly you recognize. I do remember there was a startup, I think it was an Israeli company, that used as a basis some academic research in the area of emotions in audio, so emotions expressed by voice, and I don't remember the name of the company off the top of my head, but they did commercialize this technology for emotion detection from voice. I'll see if I can find. I couldn't remember the name. It came to mind recently as I was talking to someone, but I could not remember the name. If it comes back to me, I'll.
There's another question from the same person. So some call centers are now offering the ability to automatically identify a person. Just wondering if you could comment on how this is done from an algorithmic point of view.
Yes, so there could be, I see two pathways. So one pathway would be when you are on hold, you're still recorded. So there could be for example, a chatbot that will ask you, could you confirm your name? So first of all, when you call, your number is already part of the information that the call center has access to. So they will know your phone number, which will be used to prefetch your details. Then the chatbot will ask for your name, your first name, and then date of birth and other points of verification. And as you say them, it will transcribe them and verify that this is what is in the system. So this is one way of authentication. I'm fairly sure I saw in the news that Origin Energy uses, they set up the entire Amazon Connect and Amazon Lex, all of their systems for authentication. I saw this in the news back in July, I think. So this is one example. Another example is where you use your voice as your fingerprint. And I assume they would also map all the voice features, so fundamental frequency, all sorts of voice features that you can think of. I think it's like 100 different features that can be used, and this would also be matched to what they have in the database. So this is another example, and this is something that I was saying as a biometrics. Use voice as a biometrics is probably not a great idea.
Great. And then there's one last question. What was the name of the library that allows detection of PII?
Microsoft Presidio. So it's on GitHub. Presidio. And it's one of several. Any more questions?
No more on here. So I think given the time, we might wrap up. But thanks everyone for coming, and catch you next month for our next one, and keep your eyes peeled on the page for our next topic and presenter.
Thank you.